So I've had some miscellaneous requests. Feel free to leave if you want to. I'm going to record this and email you all when it's done. I'll just give that back to you. So, my miscellaneous requests were induction. There's a whole seminar on that. But I did have planes, so I'll just have a quick chat about that. Okay, planes in 3D are not different from other things anywhere in that they are collections of points. And there are multiple ways of representing any collection of points. In the same way as curves. One is the parametric form, which tells you what all the points on the curve are, and the other one is a Cartesian form, which tells you what all of the whether a point is on the curve. Planes have those two versions as well. An equation like that is a Cartesian equation for a plane, and it will allow me to tell whether a point is on the plane or not. You know, I could pick a random point 1, 1, 1, and it wouldn't be on that plane because when I do 1 plus 3 times 1 minus 2 times 1, it doesn't come out to 7. But thinking of points that are on the plane there is a bit trickier. Maybe 1, 1, minus 3 on 2 would do the trick. So if you pick two coordinates, you can usually figure out what the last coordinate has to be to make it come out to the right answer. So, yes. But these are not good. They're difficult to find what their points are. So you can also do them in parametric form if you like. And parametric form of an equation has a tendency to look like this. It'll be like a point. I'll just do an example first. Something like that. It'll have a point and a t and an s and two vectors. That's what your parametric form of a plane tends to look like. So if it was just this, that'd be a line. Okay, if it was just a t with one vector, that'd be the vector version of the parametric form of a line. But the reason I need two of them is because a plane's a two-dimensional object. So I'll start at this point and I'll head in two different directions and that will produce the plane. Okay. This one is good for telling what the points on the plane are. This says that no matter which t and s I pick, it'll make a new point on the plane. This one's good for telling whether a point is on the plane. But as with all representations using algebra of physical objects, well, not necessarily physical, but, you know, imaginary objects still, but of physical objects, there is information you can glean just from the equation itself about the object. So there are things I can say about a plane that I can get from these pieces of information. So things I could say about a plane are the points that are in the plane. So, things to say about a plane. Points in the plane. So if you're in parametric form, I've already got a point. 103 is in the plane. Sweet. So the plane represented by parametric form above has 103 in it. It's not really that special, that point. I mean, I'm just choosing t equals 0 and s equals 0. I could choose any numbers I wanted for s and t and it would give me a point in the plane. That's the whole point of the parametric form. But you can read one of them off just by staring at it. Okay, so that happens to be one of the points in the plane. 115 is probably not a point in the plane. It is a vector which is in the plane. So what's the other thing you could do? if you wanted to come up with a point of the plane that was in Cartesian form, oh, I should just put a little star here. These are not the same plane. Okay, just pointing that out. I didn't attempt to make them the same plane. 103 is not one of these points. 1 minus 3 is, but there's no guarantee that the rest of them are. Okay, the plane represented by the Cartesian form above, that's a bit harder. The usual way is to say, well, let's just choose, you know, x equals 1 and y equals 0, say. Doesn't matter what you pick. And then you'll have 1 plus 3 times 0 minus 2 times z equals 7. And you can solve that to figure out what the z has to be. So 1, 0 minus 3 is in the plane. So you can always, if you have a Cartesian form, find points by picking two coordinates and figuring out what the third coordinate has to be to make the equation work. That's a way of finding points. Now, I do not want you, I would feel very sad if you remembered that as a procedure. Okay? If you do, then, you know, that's fine, but I'll feel sad. But I would prefer it if you sort of kept in your head that the Cartesian form tells you where the points are on the plane, so that means if I pick some coordinates, I can figure out how it has to be on the plane by subbing them in. Okay, so you can always find points inside the plane. That's great. The other things you can say about a plane is its normal vector. So, in 2D, a line has an equation like this, if it didn't have a z. If this was in 2 dimensions, x plus 3y equals 7 would be a line, and that line would have a slope, and you're used to that slope being a number, a single number, which in this case would be minus a third. If you rearrange that to get y equals, you could tell what the slope was. Planes are a bit more tricky than that because you're in 3D, so if you go in any direction, it'll have a different slope. So if I've got a plane like sitting like that, if I go this way, the slope is down. If I go this way, the slope is up. The slope is 0 in this direction because I'm not going up or down at all. Every direction has its own slope, so you can't use a single number to talk about the slope of a plane. But what you can do is use the normal vector. The normal vector tells you about the slope of the plane because there's only one direction which is perpendicular to everything in this plane. No matter where I put that vector that's perpendicular, it's in the same direction. So that's what the normal vector is supposed to be. It's like the slope in inverted commas of a plane. In 2D, you can do a normal vector as well if you want. But you're used to talking about slope in terms of a number. But we can't do that in 3D. And so if I was in 17 dimensions, I could talk about the slope of a plane, of a hyperplane as well, and it would be a vector. Okay. And this is the magic trick. So a normal vector to a plane is a vector that's perpendicular to everything in the plane, every vector in the plane. So it's perpendicular in the plane. And obviously, or maybe not obviously, but you know, there are infinitely many vectors that are perpendicular to the plane because I could just make them longer by timesing them by 2 or something, or 7 or minus 16. So there are infinitely many vectors perpendicular to the plane, so it's not really true to have the normal vector, there's just a normal vector. But a really nice place to find that vector is in the Cartesian version of the plane. So if you have something like this, then these three coefficients, 1, 3 and minus 2, is a normal vector. I could just as easily have multiplied the whole equation by 17 and it would give me another normal vector. But that normal vector would just be a multiple of that vector, and so parallel to it. So, and it works backwards. If you have a normal vector, you can construct the equation of the plane from it. Well, an equation for the plane from it. And that is really the big idea of planes, is that they have normal vectors, and normal vectors tell you the slope. And that I can tell what the normal vector is by looking at what a normal vector is by looking at its Cartesian equation. In the same way that if I rearrange the equation of a line in the right way, I can tell its slope just by looking at what number's next to the x. If I rearrange the equation of a plane to get variables equals number, then that will tell me what the equation of the plane, what the normal vector is. And the other thing is that parallel planes have the same normal vectors. Because the normal vector describes the slope of a plane, it should have that property, that two things with the same slope should be parallel, and that's true. If they have the same normal vectors, or the vectors are multiples of each other at least, but the same collection of normal vectors, then they are the same the slope and therefore parallel. The difference will be this number at the end here. If I had x plus 3y minus 2z equals 5, that would be a different plane, but it would be parallel to this one. Yes?
What if you have planes that are perpendicular to each other?
Planes that are perpendicular are really difficult to describe because perpendicular planes still share a whole line's worth of points. There is probably something about their normal vectors, but we're in 3D, so it's really difficult to talk about. Probably. The dot product of the normal vectors would probably be 0, but I do not trust myself to say that that's true. Let's think about it. We have two planes. Normal vector here, normal vector there. Yeah. In fact, all the vectors... Quite a few of the vectors in this plane are normal vectors for that plane. Interesting. I think their normal vectors will be perpendicular as well. That makes a lot of sense, but I don't trust it because we're in 3D and weird stuff happens. So, yes. Okay. I don't think you've been talked to... I think that would make sense. Right. So, parallel planes have the same normal vectors, which means that now we have all the information we could possibly need to figure out the Cartesian equation of a plane from various other bits of information. Except that the very, very useful fact that if you take two vectors and cross-product them, then the result is perpendicular to both of them. That's a very useful piece of information that allows us to find the equations of planes. So, basically, to find the equation of a plane, you need a normal vector, which will give you the coefficients of x, y, and z, and then you need just one point on the plane to tell you what this number is. Because once you have a single point on the plane, you know that all the points on the plane will satisfy the equation, so they'll all have the same number when you sub them in. So you just need one of them to tell you what that number is. So to find the equation of a plane, you need a point in the plane and a normal vector. And that's what you need to find the equation of a plane. You know, your normal vector you may have to find by some other methods, and you can find a normal vector if you've got two vectors in the plane, or a point and a vector, or 3 points. All of those informations can tell you what the normal vector is, but you might need that information. You don't technically need that information. You only need it to get to the normal vector. So, e.g., equation of plane through the point 1, 0, 3, and the line 2 minus 2, 0. Let me just check something. That would be a 1, which means that would have to be 0. Okay. Yep. Okay, good. Just making sure that point isn't on that line. Otherwise there'd be infinitely many planes through that point in that line. Okay, so to find the equation of a plane, you need a point in the plane, which we have. Sweet. But you also need a normal vector to the plane, which we do not currently have. Yep?
Could you, so you could say that you need 3 points on the plane, so it's a nice place to start, and you've already got 2. And then could you just sub in some value of t that isn't 0 and get a third point?
Okay, so what we've had as a suggestion is that I can use 3 points in the plane to find the normal vector, and I've already got 2 points in the plane. This point's in the plane, and this point's on the line, and the line is in the plane, so that point's in the plane too. And you could use your t to get another point on the line, which would also be in the plane. Okay, that's a good idea. However, we do not need to do that much work, because what we need is to get the normal vector by a cross product, I would need 2 vectors that are in the plane, and this vector is already inside the line, and the line is inside the plane, so this vector 2 minus 2, 0 is in the plane already. So I don't need to get a third point because I've already got a vector. All I need is another vector. If I can have 2 vectors, I can cross them and that'll give me a normal vector. So these 2 vectors here could create a vector in the plane. So I could do 115 minus 103, which is probably a better one to do because it would give me less negatives. Nothing would have stopped me doing the other one. I just need any vector in the plane. So that is a vector in the plane. We have another vector in the plane, which is 2 minus 2, 0. And I need a vector, a normal vector will be perpendicular to both of them, so it could be the cross product. Now let me see. So 1 times 0 minus 2 times minus 2 would be plus 4. 0 times 0 minus 4, but we have to negative it. And 0 minus 2. Alright. That's my cross product. Now, any multiple of that will do, so I could divide that one by 2 if it made me feel better. But there's nothing that I need to do that with. I think that's the cross product. I did all of the little determinants. So that one, but I have to minus it, and that one to give me the 3 different coordinates. Cool, and so the equation is 4x plus 4y minus 2z equals some number which I do not currently know. I'm probably doing this differently to the way the lecturer does it. I'm sorry. I'm not sure. Anyway, I know the equation has to look like that. I don't know what that c is yet, but that's okay because every point in the plane will give me the same c. That's the way that these equations work. So I just need to sub in a point. I'll sub in 0, 1, 1, 0, 3 because I know that's in the plane. 4 times 1 plus 4 times 0 minus 2 times 3 equals c. And so c is 4 minus 6, which is minus 2. So the equation is 4x plus 4y minus 2z equals minus 2. Done.
If you hadn't taken that common factor of 2 out before, would you still have the same p?
No, I wouldn't. I would have a minus 1 here.
Yeah. So you could still take a common factor out now, but take out everything.
Yeah. So you're right. Either if I had taken a common factor out of this one and made it 2, 2 minus 1, I would have gotten 2, 2 minus 1, but then my c would have come out as minus 1, and it's the same answer as dividing all of this by 2, so it doesn't really matter.
So we can leave it either way.
Yep, either way. But most mathematicians would feel really uncomfortable with leaving something that has a factor of 2 in everything. And so they would just, it would not be wrong, it would just, you know, it's this sort of sense of, it's like an OCD sort of thing. Yeah, they don't like that. I don't like that. So, I mean, I would have done it earlier. I would have done it here and divided all this by 2. So, at this stage, I would have done a triple equality, which is equivalent to, and done 2, 2 minus 1, and from that point figured it out from there. But it doesn't really matter. I would have written which is equivalent to 2, 2 minus 1.
Can you put down it?
Which is equivalent to, which has three lines instead of 2.
Is that the same as the one with arrow?
No. You mean this one?
Yeah.
No, that means which implies that, and you can't put a noun after which implies that without a verb as well. And so a single point is a noun and can't go after an implies sign. So what I'm saying is that this is a normal vector, and I could equivalently use any multiple of it. And so I use the symbol for objects being equivalent, which is the triple equal sign. But it's sometimes people use a different symbol for that, because that triple equality sign can mean different things in different contexts. In this context, yeah. Well, you would have put a whole other sentence saying, alternatively, this. That would be what you would say. Yeah. Or, the word or is a good word. Yeah. Okay. If you want to know where a line meets a plane, then you need to find which point on the line is also on the plane. And that can give people a little bit of trouble sometimes. Where does the line that meet the plane? I don't know. 5x minus z equals 6. Let me just check something. Okay. Yeah. Okay, good. The int 4, 8, 5. All right. The whole line isn't in the plane. I was just checking, otherwise I would have that would have been distressing. Okay. So at the moment this line is written in vector form, which is parametric. It's telling me what all of the points on the line look like. It's much easier to tell where a line meets a plane if the line is in parametric or vector form. If it's in Cartesian form, that's trickier. Where does that line meet that plane? It's easier if you have a description of what all the points on the line are. The thing is that to be on the line, it has to have a format like that. There must be a t that makes it the point. And to be in the plane, when I sub it into that equation, it will work. And so to be on both of them, it will have to have that format, and it will work when I sub it into there, which is telling me exactly what to do. It tells me to sub that into there. So points on line of the form 170 plus t of 315, which is the same as 1 plus 3t, 7 plus t, 5t. That's putting the t in there and then adding them together, turning it into its parametric form as opposed to its vector parametric form. And we also know that points on the plane satisfy the equation. I mean, those are the truths that we know. They are the fundamental truths about the way our coordinate geometry works. One is a description of what the points on the line are, and the other one is a description of whether they are, so I'll sub it in. So I've got 5 times x, which is 1 plus 3t, minus z, which is 5t, must be equal to 6. If this point is on that plane, then when I sub this into there, it'll work. And so I got 5 plus 15t minus 5t equals 6. So 5 plus 10t equals 6. 10t equals 1, subtracting the 5. T is a tenth. So the point is 170 plus a tenth of 315, because that's what the t works out to be after all. Which is, I suppose, 1 3/10, which is 1.3. 7 1/10. And a half. Because 5/10 is a half. Ta-da! You could have used decimals, but for some reason mathematicians don't like decimals, so fractions are the go.
Now you can sub back into the plane to check.
Yes, I could check if I've done my algebra right, just to check finally. 5 times... What was my equation? 5 times 13 tenths minus a half is 13 over 2 minus a half. 13 over 2 minus 1 over 2 would be 12 over 2, which is 6, which is what it's supposed to be. So I haven't made an arithmetic mistake at this point here. All right, well that's everything that, for now, I want to tell you about planes. Cool. What else was on the list?